Okay, good morning everyone. Thanks ever so much for inviting us to come and give you this presentation. We've been doing these for maybe about a couple of years now for different universities, but we've been doing them mainly in lockdown, so we've been doing them over Zoom. So this is the first time we've actually had a chance to come and do something face to face. So we're kind of excited about it, and it's also something that might go wrong. So please bear with us because we've not had this three-dimensional interaction with our audience before. Just to give you an idea about the structure of the day, we've broken it up into three sections. We're going to talk about learning outcomes. We're going to talk about teaching at scale. We're going to talk about remote practicals. But before we get going, we're going to do a little bit of an introduction. So we're going to introduce who we are, why, what we're trying to do both within the University of Sheffield and externally, what we're hoping to achieve today, and then we have a warm-up activity. So I'll just introduce myself and then I'll pass over to Adam. So I'm Andrew, and I'm a professor of of engineering education, and I'm using that title because I've only been a professor for 5 months, so I'm still really excited about using the term. And the thing that I really like about teaching engineering is simplicity. I really like taking what a lot of people consider to be very complex problems and finding a way to simplify them down until the point where students go, I get that, and then increasing the complexity. And I also really like simplicity in the way that we do teaching. So quite a lot of the time, I think that we overcomplicate things that don't necessarily need to be as complicated.
Excellent. Yes, good morning, everybody. My name is Adam, and I work in the same department as Andrew back in Sheffield. And my responsibility is teaching labs and practical sessions in computing, control systems, and electrical and electronic engineering. So that's my kind of space. Andrew's much more on the mechanical side, so between us we're covering quite a wide range of engineering. And my big passion in engineering, I suppose, is the application of things. So I started out as a physicist and then realised actually I want to do something that has an impact on the world, has a point to it, has somewhere to go. So sitting in this department where we do practical teaching, we're taking all of that theory, all of that fundamentals, all of that basic engineering science, and getting students to do something with it hands-on and see where that takes them. So that's my passion. That's us. Thank you.
And what we are trying to do is professionalize engineering labs. And I think for a very long time, labs have been what we call the kind of the Cinderella of the engineering programs. Everyone that you talk to in engineering education tends to agree they're really important and they have to be part of an engineering degree program. But when you ask people to sort of articulate what their philosophy behind how they're delivering those labs are, people tend to kind of fall apart at that point, and they know they've got to be there, but they haven't invested as much time and effort into thinking about why they're involved in the program as much as some of the other things. So there's lots of learning and teaching community about things like employability and decolonializing the curriculum and all of these other things that are very fashionable at the moment, but labs seem to have kind of been overlooked, and they're doing all the work, and I think they need a bit more of the attention, which is what we are trying to do, is to go out to other universities and help people to kind of revolutionize and reinvent the way they do labs and just give them the attention that they deserve. And we've also got our mission statement up here. So this is for our particular department, which we'll talk about later, but I'll just leave that up there. That's what we are trying to do internally at the University of Sheffield. And I wonder whether or not that's something that you would think would be that you would potentially want to achieve as well. And we're going to move on to a warm-up exercise.
So here's the aims that we came. So when we started talking to the team here at Trinity about what's covering this session, this is what we came up with. This is effectively the learning outcomes for today. You've probably already seen them. I won't read them out. Just give you 20 seconds to skim through what you all should be able to do by the end of today's session.
Now's your opportunity to leave if this is not what you're here for.
objective. So that's the plan. That's the plan for the whole session. What we plan on doing, as we said, we split it into 3 parts, but it's going to be very interactive. So there's going to be 3 parts, and each of those 3 parts will have an exercise for you to do, because we want to know how you currently deliver labs and what you want to get out of your labs and practical exercises in the future. Then hopefully we'll offer some solutions or some ideas, because as we have said, we focus on labs. This is our primary function, is to deliver practical training. We've got a lot of experience, so we can offer you some solutions from our practice that will help, with the caveat that we don't know everything. So actually, if you've got great ideas you want to share with us and with the group, we definitely want to hear that.
Problems that you've encountered that we've not, that we could help you work with to find solutions for.
Absolutely. Just do this one.
Yeah. This is the last of the introduction slides before we actually get onto some proper work. And I thought this was useful because as we've said, we spend a lot of time thinking about labs, and one of the bits of confusion that's cropped up is that what terms people use to describe things can actually be quite convoluted, and sort of things can be interchanged without really knowing it. So, for example, if I asked you what a lab was, some people might say, well, that's a room. Some people might say it's a thing that students do. Some people might say it's a piece of equipment. So what we tend to do in our department is identify names for things and stick to them. So we're going to call in this session, the lab is the room that the students work in. A session is the start and end time that would be in their timetable. An activity is the task that the students perform when they're in the lab during a session. We're also going to talk a bit about learning outcomes. So I'm going to use some nomenclature to talk about how programs tend to be structured. So a program is the same as a degree course. It's what students would go out with a qualification with. A module is what we call a kind of a component of a program. So most programs are broken down into components, and they've all got different names at different institutions, but we're going to call it a module. And then a practical activity are the things that are embedded within modules typically. So a lab class might be an activity that happens within a module. Okay. And so this is the first of our bit of work that we're going to do. And we're going to talk a little about learning outcomes, and we've then got a practical activity for you to engage with. So thank you, Adam. When we started this, what we wanted to do was get a little bit of a feel for what you do. And we sent out a form and got some responses back, and those are going to feed into the activity that we've done. So I've printed out all those responses, and that's going to form part of the workshop that we're doing today. Of the people in the room, we got 9 responses back for different reasons why you think people or students would go in the lab. And of those 9, 6 people agreed to send us some information about what you're doing, some lab sheets and things like that. And 3 people said they either don't know where to find that information, or they don't have access to it. And I think one of the problems with the coherence that students feel for laboratory exercises kind of relates to the fact that when we compartmentalize this teaching and give it to an academic to do, they don't really necessarily know what other academics are doing. So that kind of helicopter view of what's going on across all the different labs can sometimes get lost as a result of delegating jobs off to different people. So I thought that was interesting of itself, that there are people who go, well, I don't know where to find this information out. It's somewhere in the system, but I don't have access to it, or I can't find it. So some observations that we have from the lab sheets that we were sent was generally, compared to other institutions that we've seen, the lab sheets are very clearly laid out and very well presented in terms of the instructions that students have got to follow, the kind of the objective for why they're in the room, what the procedure is. What we also noted was that the learning outcomes weren't immediately obvious on some of them, and some people have confused learning outcomes with the task that students were supposed to be performing, rather than what they were expected to learn as a result of doing that task. So that's some interesting takeaways from the stuff that we got. Is actually, as a student looking at your material without any context, I was unaware of what I was supposed to be taking away beyond actually just the execution of the tasks. But this was just an overview. As I say, all the data that we got back is going to form part of the exercise. Thanks. Okay, so learning outcomes. one of my big bugbears about learning outcomes is that they get talked about all the time in engineering, learning and teaching. We tend to think that they are really good. Whenever we talk about pedagogical stuff, we always talk about learning outcomes. But I very rarely see anyone thinking about how they all mesh together. And one of the reasons I think we really like learning outcomes is that as STEM practitioners, it's really nice to turn this kind of messy, convoluted thing that we call teaching into something that's predictable and is a system and that we can measure the output of, because people who do science like to measure things. And if we've got a defined aim and it fits into a system, that sits better than saying we've got a student that's got a bunch of complex learning needs. So I think that's why we really spend a lot of time on learning outcomes. But as I say, I think that what we don't do enough of is think about how those learning outcomes relate to one another. And I think in my next slide, I talk about some of the complexities. These are why learning outcomes are not simply as straightforward as just saying, for this activity, I would like this student to learn X, which is relatively straightforward to write down. But when we are thinking about writing what those learning outcomes are, they do exist at a variety of levels. And I'll talk about that a little bit in the next slide. But we've got things that can be very broad or things that can be very specific in terms of what we want students to do. They're often distributed across lots of multiple systems. So if you've got a lab sheet, if you've written your learning outcomes on that, does that live in your student programs software? Does it live on the program documentation? And if you wanted to find out what a learning outcome is for a particular lecture or a tutorial or an assignment, how would you necessarily find that? Is that all in one place? Certainly at Sheffield, it's not that straightforward to find out what everybody else is doing and what the aims are. Programs are complicated. So quite often, especially as students get into their final years, they're doing optional modules, they're doing different activities, they're doing different projects and things like that. So programs, co-requisites, prerequisites, all of these things make programs particularly complicated. And of course, students are complicated as well. So students miss things and engage with some things and don't engage with other things, and can have particular individual issues with engaging with the material. So how do we know that what they are getting is reflected in what our program documentation says in a rigorous way? And I think that they're also demanding more flexibility. So if a student misses an assignment, sometimes people in programs offices say, well, they've done really well up to this point, so we'll just kind of smooth the marks across that assignment because they don't have time to do that one, or something like that. Actually, can we be more flexible in allowing students to choose what they focus their attention on in a way that doesn't become unnecessarily complex for us to design? And the final one is, of course, usually engineering and science subjects can be accredited. So we need to be able to rigorously defend every student's activities to meet their particular learning outcomes. So doing that is a challenge in and of itself. But I would say with all of these things, learning outcomes aren't that difficult. They're not that complex. We can just write a learning outcome and say, this is what I want my students to do when I have my contact time with them, or this is what I want them to do in the assignment. What makes learning outcomes really interesting and complicated is the relationship between those learning outcomes. So I almost don't care what learning outcomes are. What I'm interested in is how do they connect together in a coherent way for the students. Yeah. So thank you, Adam, and feel free to jump in at any point if you think I'm misrepresenting us. This is my sort of typical representation of how the different levels of learning outcomes can be arranged. We have activities that students perform. They are generally nested within modules, and these things are nested within programs. So for each learning outcome, it's got a different level. It could be the thing that the student is doing that day, the thing they are doing that semester, or the thing that they're doing across their degree program. But as you'll see, the number of learning outcomes that you get reduces as you go up the tree. So as you get to a program level learning outcome, there's a lot fewer than there are activity level learning outcomes. So something is happening there. Either we're losing them along the way, or more often, they're becoming broader. We're losing that detail. So for example, like this linear relationship loses that specificity of what we actually mean when we are assessing those program level learning outcomes. Okay. So when I put this slide up before, I was showing Adam, and he goes, "So what? What's this got to do with labs? This is a labs workshop." Okay, and I think the why this is really important for labs is that if we have lab skills embedded within our modules, these are the kind of things that can get dissolved away as we broaden things out. So if we've got an activity within a module where a student is going in and, say, using an oscilloscope, in a module learning outcome, that might be something like gain experimental skills. And what you will end up with is gain experimental skills appearing in all the modules, which then turns into a program level learning outcome of being employing experimental methods. And if you ask a student to say, are you gaining these kind of are you learning about experimental methods? They go, yes, I've got a program level learning outcome. What does that mean? Well, I don't know, because it doesn't mention it in my program. I've got to actually go down and drill down into the detail, but that's all been lost as we increase this breadth of learning outcome. So if you want to, for example, say how all of these learning outcomes relate to one another, it's very difficult to do with this simple linear nesting with this traditional view. And why this is quite important is we need to communicate what's happening here and here and here and here between not only the members of staff, so that when members of staff are delivering this module, they're aware of what's happening down here, and there's that natural follow-on, but also for students, either current or prospective ones. I want to be an experimentalist. What does that mean for me? Well, you'll do a bit here and a bit here and a bit here and a bit here. How do they marry together? What is this building? What is the overall picture that we're building from each of these individual activities? And if we define that explicitly, we can give students a very rich picture of what they're going to be as an experimentalist. But if we define it just as a program level learning outcome, it becomes meaningless, because it will just say being hands-on or being practical or something. So I'm going to present to you an alternative view, which is my learning outcome mapping. And what I believe it's easily possible to do is to look within our programs at the activity level and find out where activities have these natural relationships and document that. It doesn't have to sit within our program regulations. It can sit outside of it for purely internal use. But when we say to our students, we've got we will teach you to be an experimentalist, we can define all the different learning outcomes that we have thought of about what we feel an experimentalist is, and they can map and audit their skills against the different labs that they're doing and show how that skill set is being incrementally built up across all of their different activities. But it doesn't feature in any of our module learning outcomes because we don't have the space to do that within this linear nesting structure. So we can do this, and I've created this term called meta module. So a meta module can thread between all the different modules and pull out different activities, and all it is a collection of individual activities that have got some sort of natural relationship to one another. The other thing that I put on here is learning opportunities. So when we go into labs, when we put our students in labs, there are things that we want students to potentially do that aren't explicit learning outcomes. Things like learning through failure, tinkering, all of these things that we think are really important, but we wouldn't necessarily write into our program regulations because they're too difficult to assess. But we want them to be part of our programs, and we want to make sure that everybody on the program knows that students have got lots of opportunities to do these things. But how do we map that? So this is a meta mapping that you can put on top of your program. Okay, so on that vein, what I'd like you to do is to work in pairs of tables to have a think about what these meta learning outcomes could be for your for the learning outcomes that you've sent me. So I have got in various recycled envelopes somewhere here. Printouts of all of the things that you have sent me. There we are. Yep. These are envelopes from my house. on here, I've printed up different learning outcomes. So on the white ones are the ones that you have sent me. Okay, these are the ones that I got from your forms that you sent. These are the reasons we put student in labs. They might be what I would call learning opportunities. They might be activity level learning outcomes. They might be program level learning outcomes. What I'd like you to do is try and arrange them, look at them and see how you think that they all relate to one another. The light grey ones are what we call our engineering graduate attributes. Some of them might be related to experimental things, some might not. And the dark grey ones are what are our practical learning outcomes. So these are the kind of meta learning outcomes that we have defined, and I thought I'd throw those into the mix just for you to kind of have a look at. So what I'd like you to do is look at each of the items and consider kind of what level is this? Is this something you do an activity? Is it a sort of a meta module, or is it a program level learning outcome? Are themes emerging? Are lots of people saying the same thing? Can you cluster them together and say this is actually a thematic reason for putting students in lab that we can thread across multiple different activities and reinforce that learning? And if there are things that you think are missing or at any level, feel free to add them in. There's a few blank ones in there. There's also post-it notes, and see if you can develop something that looks not exactly like this, but have a think about how the things in here might relate to that mapping. I'm not expecting you to finish this activity. This isn't, you're not going to walk out of here having a perfectly mapped practical program. What we're doing is giving you a tool so that this activity can be repeated with the people in your institution that are interested in doing this, and just showing you this is basically the activity that we did in order to develop our learning outcomes. This is just to give you a kind of a practical go at how you might consider identifying these learning outcomes and then mapping them. Okay. When I did this for our department, I started, because we'll talk about this a little bit, but our department only does labs. I talked to our staff about what they thought labs were for and what skills they feel that that we should be giving to graduate engineers. And we have a multidisciplinary range. So we have bioengineers, civil engineers, mechanical engineers, the whole range. And so actually what we were looking for was getting that expert input, because the accrediting bodies and the program level is just going to say, be an experimentalist. Yeah. So basically you can say anything, but what we want to do is say, what do we think that means, and define that. So I started more at the bottom level and then tried to map what those skills are.
Then you went back, let's say, and you looked at what the program outcomes were and said, this is where these ones fit into it, and this is where they do, and actually we're missing.
Yeah. Because as I said, as the program levels, as you go up, these get fewer and fewer, and they become more and more broad. So actually anything you do down here is probably going to conform, but actually the heart of what the student's experiencing is actually down on these activity levels. And if you want to define yourself as an institution and you say, we want our students to be really practical, it's actually these things that are important and these relationships. So we had a really good discussion over here about health and safety. That was one that was picked out. Okay, so there'll definitely be a program learning outcome that says must be aware of health and safety, or be able to do health and safety, something like that. And any module that's got a lab in it will have some sort of health and safety component, but you're not going to have a module level learning outcome that says has got to do health and safety, because it would be in every module that's got a lab. It would just get too big. So this is a perfect example of where you could pull health and safety out as a sort of meta learning outcome and internally map it so that you know from all your activities where that's happening, so that as from an overview point of view, you understand where health and safety is happening, but you don't necessarily need to make that part of your program rates. So I guess the question would be, this seems like an awful lot of bureaucracy. It's like, why would you map all this stuff when it's not needed? Okay, the accrediting bodies are probably happy with this. Everything will work. Well, firstly, it does provoke these interesting discussions, which I think is really valuable. So these sorts of things about what we actually think a practical engineer is. There's a lot of consensus, but there's also a lot of difference. And having those discussions, I think, is really valuable. But there are also lots of other advantages for mapping in this sort of way. So we can actually capture this complexity of learning outcomes, and this model will capture the fact that we've got all these different levels. And it's a way of communicating not only between staff but also with students. So how do students know when they get there in week one what it means to be a practical engineer? If you say this is your path that we've defined for you, these are the things that we think are valuable about being a practical engineer, and these are the activities where you will build up that skill set, they know that you've got a coherent package of work that is leading somewhere. But also, if you're delegating jobs off to different members of staff in different modules doing different bits of teaching, everyone can be on the same page about where their teaching fits into the broader program. Students can self-reflect and audit. Student knows what skills they're picking up if you've articulated it. They can look at themselves and go, I did that activity and I was supposed to be learning about health and safety. I wasn't very good at that. I might, think that I need to put a bit of work in there. When's my next opportunity to do that? Well, if you've got all these things mapped, you can use it to know where students are going to receive feedback and apply their skills the next time. The whole point of feedback is that you can get better the next time you apply it. If we're just doing health and safety as a one-shot deal, you come in, you do the health and safety lab, bang, you're done. Here's your feedback. When am I going to use that next? If you've got a map of where all of these things are happening, they can use that feedback and know how to improve the next time. And that can be, not just health and safety, but anything that's a practical skill. And of course, you can map other things, these learning opportunities. If you say we want our students to have a bit of competition, we want them to experience a range of learning styles. Unless you've actually got these things mapped, you don't know whether or not one academic is using the same learning style as another academic and another academic. So actually saying we want a balanced diet of all these different things, we need to have that visibility of what's happening at the activity level so that we can make sure that's balanced. And of course, accrediting bodies can come in. If you say to them, if they say, we want to know where you're doing health and safety, if you point to the program level learning outcome and go, it's there, it's at the top. They might go, well, what's happening on the ground? If you can say, actually, in activity 4, 7, 9, and 12, this one is where they do PPE, this one's where they do risk assessment, this one's where they do chemicals. They're going to smile, and they're going to accredit you, and they're going to walk away, and you're not going to have a hard life. So this is, I said before that learning outcomes are actually quite easy to write. And what I really want you to take away from here is it's the relationships between those learning outcomes where the power lies in creating a coherent curriculum. But actually, the learning outcome framework that I presented to you is fairly straightforward. It's just one picture. It's quite easy to kind of implement if you want. What is much harder is building this into a culture. Okay, if you want to have a coherent message across a group of academics to say, this is our philosophy for delivering the practical teaching for our students, this bit of the curriculum, you are going to be doing this because as a jigsaw, your piece has to fit into the bigger picture. That can be a leadership challenge. Okay, and how you broach that is a whole other subject, but I'd say the key is a good balance between being consultative, like doing these sorts of activities where you get people around the table, get their opinions, but then a bit of decision making and go, your opinion was brilliant and really important, but actually in the bigger picture, this has to have less focus because if we focus on this, we're not creating balance for the students. So if you're doing these things, make sure that you're consulting and building that culture of practical being really important. Okay, I think that's me done. There was one more activity, but I don't think we really have time for it because we're overrunning slightly. This was something else that I was going to do, which was a sort of sticky dot exercise, but I'll give you the idea so you can take it away, which is actually of all of these learning outcomes, are the ones that we think are right for labs the right ones? Could we assess them in the classroom or in an exam or deliver a lecture on them? Or would they be better suited to a lab? So sometimes we think that some things are better taught in a lab, but actually they're not. So actually just run a rational analysis over that. And I like the idea of having two colours that when they mix together form a blended one, because actually it might be the case that you want to do some things in the classroom, some things in the lab, and actually when you blend those two things together, it's very, very powerful. Health and safety, you probably want to do it in a lab. Report writing, maybe it's this one here, because actually the subject of report writing might be taught in a lecture and then applied to a lab class. So that was what I was going to do, but we don't have time for that, but you can take that idea away and I'll pass over to Adam.
Yes, excellent. I shall start on this one. So linking on from what we've just considered is that to pull off this kind of mapping requires oversight of everything that's going on, and it is a big challenge. We don't want to underestimate it. Everyone can contribute, so whether you just run a few labs in one module or you deliver a selection of labs, or you are responsible for a program, everyone's got their piece. But to pull off a big mapping exercise like this it's got to be done at scale. It's got to be done in a large form. So our next little section, if you like, is about how we deliver practicals at scale at Sheffield, and which tell you all of the advantages of this, I suppose, but then look at what the challenges are, what the challenges would be if you were to implement something similar for yourselves. So here is, there we go. Here is a kind of example of traditional lab teaching. There we go. Here's an example of traditional lab teaching. So I went for mechanical engineering because it's fairly general, but imagine that your blue box is your physical space of a mechanical engineering teaching lab. And inside there, you might have 3 bits of kit for teaching fluids, some kind of network of pipes and pumps and things. You might have a handful of dynamics kit where you can do some load testing and things, thermo kit, boilers, condensers, etc., and some electronics in the corner, because even mechanical engineers need to know a little bit. But you've only got maybe 3 of each of these sets of things. They're not necessarily the best in the world because it's mechanical engineering does a little bit of everything. And they're not necessarily led by specialists in that area. So mechanical engineering academics may not be teaching the lab associated with their specialism. So teaching labs in kind of the traditional way that we see pretty much everywhere. This isn't aimed at any institution in particular. This is kind of a generalization of how labs have always been taught, as far as we can tell. There's very few sets of equipment for each thing. So if you've only got 3 sets of fluid kit, that means you can only have 3 pairs or 3 small groups doing that activity at one time. So then your timetabling becomes a mess because students could be doing that any time of the year. So sometimes they do this experiment, then they do these experiments, then they do these experiments. If any of these rely on previous knowledge, goodness knows when students are going to get that. So if they're relying on knowledge from week 1 that was taught in the lectures, but they're also doing their labs in week 1, or they're relying on knowledge that's taught in week 7, but the lab came 2 weeks earlier, it's a mess for the students because they don't know where to go. And that can work the other way around, because sometimes you might introduce a concept in a lab, but the students don't see the theory for another 4 weeks, and it's a puzzle. So by doing things at this small scale, it's very disjoint, I suppose. For a single department, mechanical engineering, for example, you only have 1 cohort of students who would go into this physical space, who would play with this physical kit. Therefore, you only get 1 cohort of students worth of money to invest in what you've got. And if you've got to cover 4 different, totally disparate subjects there, that means you might not get the best quality kit in each of these cases. And if there's a large range of all of these different areas, you might not get a subject specialist teaching you that thing. This is just mechanical engineering. Think about your institutions, your faculties, your schools, and replicate this across all the other degrees. So maybe you've got an aerospace program that has a teaching lab like this as well. Maybe there's a civil program. Maybe there's a whole range of all of these kind of little bit parts of things. And everyone's doing it in these kind of little cottage industries, we could call it. Everything's very small in that scale. We do things very differently. So our department is called MEE, Multidisciplinary Engineering Education, and we sit in the middle of all of the other departments that have programs, if you like. So we don't belong to any particular specialism. We're not owned by any of these departments, but we sit right at the center, and all of these departments send their students to us for their practical experiences. So the departments might run all the lectures, they would run all of the problem classes, they would do things like computing teaching, they would run the projects in 3rd and 4th year, but for the practical lab classes that tie in with modules, they send their students to us. So we would deliver things in a slightly different way. Instead of having a lab for each of these departments, we would have a lab for each type of experiment. So maybe we could have a fluids lab with 80 seats in it, because we know it's got to cover all of these different departments. Structures lab, 80. Electronics lab, 144 seats. Materials lab times 80. So we can get to a larger scale because we've got all of these different students to service. So it's worthwhile making an investment in a bigger scale. But instead of saying we're going to have the mech eng lab that teaches all the mech eng students, we say we have a fluids lab that teaches problems in fluids. The mech students can go there, the aerospace, the civil, anyone that needs to do that kind of experiment uses that. Electronics, pretty much all of them will come into the electronics department, electronics lab at some point in there. So mechanical students could go to those labs, aerospace students to those labs. Instead of working program by program to deliver these practicals, we work kind of theme by theme in what the practical activity is, but that lets us invest at scale. So summarizing, just to, in case I've missed anything, we're one central team. We teach the practicals for the whole faculty. So at Sheffield, this is all of the programs the Faculty of Engineering offers. Our laboratories are shared across all of these different programs, but that enables us to go large scale on these things. That means we do have these labs that have 80 seats in these kind of mechanical disciplines. So I know in electronics labs, often you get the big spaces, but actually mechanical labs, we can go large as well. But it also means that as teaching staff, we have oversight of everything that's going on. So I mentioned earlier that traditionally lab teachers might not be experts in what it is that they are doing. Now, in that fluids lab, you can have an Andrew who is an expert in fluids and can teach across the whole faculty in all those different programs. In the electronics lab, you can have me, and I can give better electronic support to mechanical or civil or whoever than perhaps they could do in-house. And then we have oversight of all of the practical. So it would be much easier for us to do this kind of mapping exercise at program level, because we've got one practical team who can see all of this. Just as we saw at the beginning, when there were quite a few people who said, I think it was a representative, a third of people didn't know where to find their lab material or where to find what the learning outcomes were for their practicals. We do, because we have one big team, we work in a consistent way, we deliver at massive scale, and we could perform these activities pretty swiftly.
Just had an accreditation from the IUT, and one of the sessions they were very interested in our labs, and we could just give them answers like that. We nailed it because we knew everything about what was happening in the labs in detail. Do you have a question on that?
Just saying, how many staff have you got?
Great question. However, what we're showing you here is for our context. So we have quite a big engineering faculty. So we've got about 6,000 UG students, and our practicals team is about 15 academics and around 30 technicians to service that number of students. However, the idea of collaborating, being a practical teacher rather than a thermodynamics teacher for mechanical engineering is the model that you come up with about how you do that might be different for your context. But so we've got 15 because that suits us. But actually, there are other ways of doing this. Birmingham, for example, who have got what they call their central teaching laboratories, share it with their science faculty as well. So they have these science and engineering labs that have got the same sort of model, but it's not exclusively for engineering. Sheffield has got a kind of reputation of being an engineering place, steel and everything. So we have we have enough of this sort of critical mass to justify this department. Yeah.
Is there research happening in your labs as well, or are these just teaching labs?
Predominantly teaching. I think it would be disingenuous to say no research whatsoever, but 99% teach. Certainly within the teaching semesters, it's full-time teaching. Because the other benefit you see to doing this is because your physical space is now shared across all of these different programs, your utilization of that space goes through the roof. So my electronics lab will be filled 9 till 5 every day for 12 weeks running. I don't know if you could say that about your undergraduate teaching labs, for example.
But our labs are then used by the PhD students as well. And a civil engineering lab would house all the basic engineering disciplines for the first year, because Trinity has 2 years common. So all the common labs are kind of in a similar way, in a sense. We don't have a department but our fluid labs are shared by everybody. Our electronic labs are open to everyone as well.
So we built new space to do this, and that actually required Provost Chancellor level leadership. So as an academic on the ground, you can't say, oh, let's reconfigure all the space, but a Provost Chancellor can. And we're just trying to show you this model. You could do this on a small scale, because if you've got a civil engineering lab, you could talk to the mechanical engineers and say, actually, does it make sense that we're doing the same thing across two different labs? So it can be applied on a smaller scale as well.
The presence of a teaching faculty in a lab makes a difference. That makes a difference. That's a difference that I've noted, because here the teaching faculty doesn't go to the lab.
We have a very shiny new building that was built for us, but I always say that the innovation is not the fact that we have a shiny building, it's the work allocation model. It's the fact that somebody had the vision to say, we want to professionalize the labs and we are going to employ people whose job it is to do that. And that can be done at any scale. But you are kind of preempting at the kind of the next activity. So, yeah.
Do you have labs that sit outside this model? Or are all your labs within this model?
So we tend to do multidisciplinary stuff, so specialist things. So material science, for example, do a load of like a concrete and really high temperature stuff in their own spaces. Yeah.
This tends to be kind of the bulk teaching you would do. So say you have modules that everyone in a cohort would take on, we would deliver that one. As it gets to kind of maybe the fourth year modules, for example, that need the really specialist, unique stuff, and the cohort size has gone down, departments might take that. And again, that's where it might be shared with the research side, for example.
6,000 was it? Was it a research?
6,000 UG, yeah.
But as I say, you can apply this idea of collaboration, sharing on any scale. That's just this scale suits Sheffield's context.
Do you also give an overview about the theoretical concept in the lab? Because like if a material science student, like suppose he needs to attend the fluids lab, but the fundamentals are not covered before that lab. So then how do you
Absolutely, absolutely. So we take a very consistent approach. So we're not going to claim we invented the kind of pre-lab, in-lab, post-lab thing because now everyone is doing that. But what we do is every single activity has pre-lab, in-lab, post-lab. So the pre-lab could either be pointing students to the relevant lectures, it could be creating material of our own that links the lectures and videos to the lab activity. And we enforce it strongly and strictly. So if a student hasn't done their pre-lab work, they may well just not be allowed through the door because they haven't prepared themselves to take part.
The other thing is with we have about 80 material science undergraduates, and our material science lab is 80 seaters. So when we plan our labs, we say to the module leader, when do you want your lab on atomic bonding? And they say, I'd like it in week 3 because I'm going to teach it in week 2 or 3. And so the thing marries up so that they have that lecture beforehand. Whereas if we have to do that lab 10 times across the semester, we don't know. So that's the advantage of scale in terms of dovetailing with theory. Yeah.
The physical storage, if you're crossing bio labs with electronic labs, it's totally different equipment. Do you have to move stuff in and out, or do you have different areas?
We've got different spaces.
Different spaces. So the mapping here doesn't necessarily map program to lab, for example. So yes, there's 2 bio spaces. Yes, there's an electronic space separately. But it's the specialist ones, I suppose, are more like the fluids lab or the thermodynamics lab or something like that. Doesn't tie into any specific program. They all might want some of that, but it's based on the topic of what the activity is rather than the program that use it.
Yeah, let's. I'm slightly conscious of time, so
I think I've sort of covered this. So this is telling you why scale is a good thing, and it's kind of summarising all the things, the reasons why we think this is a good idea. But our question was, do you think it's a good idea? And if it's not, why couldn't you do something like this at your institution? So I think it's a couple of minutes to just discuss amongst yourselves, reflect on this kind of radical idea, and then throw some ideas back at us about why you think it might not work, and we'll see what we can do to solve your problems.
So just to give you a bit of something a bit tangible, let's say you're teaching a very generic skill, health and safety. We had that perfect. The health and safety lab. You want all your students to do a health and safety lab. You want to do it at scale. How many science and engineering students have you got combined in the first year? 1,000? 800? Yeah. Okay. So you want to run that lab for 800 students. What are the barriers that you would face in order to say, I want to run a lab for 800 students? Well, so this is a small table activity. So work in your groups of 6 or 12, if you like. Come up with a list of all the barriers that you think you might face, and we will come up with our pre-prepared solutions. So take 5 minutes, maybe. Okay, if you want to wrap up your conversations now, we're we're going to do an exercise where we're going to miraculously try and preempt your answers. So we'll see how this goes.
This is the sort of thing we thought you might suggest. Are there any there that jump out to any of the teams as this was the biggest challenge we saw? This was the biggest one we faced. What's
Space, we had space as number one.
space?
Teaching time.
Okay, we'll take them one at a time. We'll take them one at a time because we might have some answers to these things. So space was the first one that we heard. We do this in a lot of different ways to deal with space. First up, I might tackle the middle one first, actually, because it's all about sharing and collaboration. So that's the primary way that this system works is getting people to buy in to this idea of collective sharing and collective working. So the solution to a space problem is often a cultural one, just as much as it is buying a load of physical infrastructure. Because hearing what it sounds like is already happening at Trinity and UCBs, you've got these kind of common first year programs and you've got these common spaces, but it's this sharing culture and this working together culture that might actually be the key to unlocking it if you already have the rooms. Homebrew sort of equipment is one that we come up with. Where are you going with this one? Do you want to...
Well, because we have a dedicated team to think about labs, the idea of looking at a piece of equipment that you've bought from a supplier, because you're using it every day, you go, well, I would make it differently. But if I'm only buying one of them, the investment of prototyping, designing it, testing it, manufacturing it is not worth it for one piece of kit. Whereas when we build bits of kit, we buy 20. So rather than spending 10,000, we end up spending 200,000. So actually, it's worth us building this in-house. We homebrew our solutions. So actually, if space is a problem, can we achieve the same learning outcomes by making something much more compact? You know, and I put on there so you can build things yourself that don't take up as much space but still fulfill the learning outcomes. If you've got a good learning outcome framework, you know what your students are there to do. Do they need that giant piece of kit to actually meet that learning outcome or not? But I've also put on for all of these, consider like actually, do I need to put that effort in? Could you collaborate with other institutions? You know, we work with Imperial. There's a guy that I know there called Peter who works with Imperial. He's developed a little flow visualization tube, which is about that big, and it can do basically the same job as my wind tunnel. And he said, yeah, just have the designs, make your own. Brilliant. We're collaborating. Get students to do some of the work. Could this be a student project? This is the problem. We want to teach this subject. We haven't got enough space. There's a student project there to engineer that solution. Open source, just look online, find out what other people are doing, rip it off. There are lots of people. We want to put more of our stuff out on open source. So it's not necessarily a problem that just you will face on your own. So that's where I was going with homebrew.
Makes sense. So then remote, without preempting the remote session, which we'll finish off today's workshop with. But remote systems take up far less space than a physical access solution. And actually, if you have this infrastructure of people and this culture of oversight of your whole practical program, your remote teaching is just as effective as your in-person teaching. So remote can be complementary to what you're offering. It can be just a total replacement. So over COVID, there was this whole rush of innovation for us to create remote labs. But if you now analyze those labs and think, well, actually, they deliver the same activity level learning outcomes. If I map together my learning outcomes across the whole program, the kind of the sort of implicit skills, team working, communication, they can be delivered in other places in my program. I could replace all of these big bulky bits of kit with 3 or 4 of them that they're all remotely accessible. And you've solved your stage problem for those big bulky things.
I just thought of something. You know, you said we were going to refer back to this and it might be useful.
You can do that now.
Yeah. When I thought I want an activity as an icebreaker, I want it to be practical. I want it to be an experiment, but it's got to fit inside the case that Ryanair would allow me to transport. This is just a homebrewed solution. It does the job that I wanted. It takes up no space and it costs me no money because I already had all the kit other than the 3D printed parts, but we've got 3D printers for the students. So I've homebrewed that. You can do the same thing on a bigger scale for the students.
Some solutions to your space problem, we think. What did we hear next? Is the second
Buy-in and collaboration culture kind of thing was a big
culture.
buy-in, yeah, I would call it that.
This is a very sort of managerial way of looking at things, but it is one of the most important things. As we've just seen, I've said it was a solution to space. It's a solution to everything. So first up, it's assembling your team. I think we're very lucky that our team is one dedicated department. If that's too much of a radical step for you straight off, assembling a team of all the people who deliver practicals, how often do they all get into the same room at the same time? Not just to think about timetabling or some administrative problems, but actually to think about delivery and activities, getting them all together. But eventually someone's got to make some decisions. So you do need some leadership. Once you've consulted all of everyone who's part of this program, someone's got to make a call. So bring your team together, whether it's, whether you can take a radical step and start a fresh academic team like we did, or you use your existing team and bring it all in. To work collaboratively, one of the great things that we have for consistency across everything is our lab sheet templates, I suppose. So every activity that any of us produce is on a nicely formatted template like this, identical across the whole faculty. So where we showed you earlier, all of those different programs, every lab that a student sees in first or second year gets a nice little booklet like this, learning outcomes front and center, and placed into our learning outcome framework of how we map things together. They're all accessibly designed, so we've got made sure that it's inclusive for all of our different learners. Everything's familiar and exciting. The other buy-in point that's overlooked because it's not very exciting, but is the systems aspect and the efficiency aspect. Because if everyone in the faculty or everyone in your whole team does things in the same way, you save an awful lot of time. For instance, monitoring attendance is the key one there. So often you'd have someone with a piece of paper ticking off names at the door or wherever you do it. We developed in-house an in-house system. It scans the student ID card, it records everything to a database, and then their attendance information gets automatically logged to their student record. We could only develop something bespoke like that because we have the scale to do that. So if you're just doing that for one lab space, your pen and paper system probably is the answer. If you scale up, suddenly these problems disappear because you can build a system that just takes away. And if you can highlight all of the kind of efficient and admin jobs that you could take off of people's hands by working at scale, they'll probably become a lot happier to buy into this and to work with you to deliver this project. Yeah.
Do you guys make use of demonstrators like PhD students who act?
We are probably the biggest employer of the graduate teaching assistants, we call them, in the university, I should think. They are a huge part of what we do. And they're probably a solution to several of the possible problems to this. Absolutely.
On that point, we have one of our academics is called Matteo Di Benedetti, and he is very interested in this space about the use of teaching assistants. And he has a framework which I'm sure he'd be happy to share with you after this event, where he's really thought about how to use teaching assistants effectively, both to get the most out of their time spent with the students, but also for their career development. So typically, and we've had examples of this outside of our department at our institution, but your anecdote, so you go with it.
Absolutely. So I won't name the department, but I went to a learning teaching committee in another department, and they were frustrated at the performance of their graduate teaching assistants because they said that the teaching assistants were turning up and they weren't interacting with the students. They weren't prepared, they hadn't been given the material. And the first thing they thought of was, this is unacceptable. Let's stop their pay until they perform better. And we've got this department and everyone's sort of nodding in agreement that it's a bad thing. So as people who employ a lot of GTAs and look after TAs, say, hang on a minute, what did you train them? Did you give them any training? Did you give them clear expectations? Did you pay them for preparation time? Did you even give them the material in advance to prepare for that? And the answer was no, because it's just a lecturer running a problem class and they expected some PhD students to show up and be an expert on all these things they haven't seen since the second year of their own undergraduate. It doesn't work like that. So that's why we develop a big old system and we look after our teaching assistants basically. We treat them as staff as much as we can do. There's an integrated program of training to deliver individual activities, which, as Andrew says, one of our team is really leading the way on a great way to train them, but also training to be teachers as well. So we work with the university level frameworks for delivering HEA accreditation in the UK. I don't know if that's something similar. It's kind of national accreditation for teaching skills. So we help them with workshops to work towards qualifications in teaching, and just really push that forward.
So are permanent people, like, you know, can the technical staff, for example, perform this
Absolutely. Absolutely. So we call our technicians teaching technicians deliberately. So when we advertise for new technical staff, we make very clear up front, this is a teaching technician role, and as well as polishing the brass, you will be expected to engage with the students, and they do. They love it. And depending on kind of their skill level and their role and what they want to do, we get them as involved as they are happy and they're capable. So for some of them, they even run the session completely. The academic will be in the room as well, but the teaching technicians can take charge of delivering the whole session.
It just sounds like a better idea because they're there every year, so to speak, and it's not like the PhD students who are doing it because they kind of have to do it as part of their PhD and they're getting funded or whatever.
Yeah.
It sounds like, you know, PhD Steve with the if somebody who's there all the time.
So this is part of the kind of the training framework that our team develop, and is kind of you pick out someone, a GTA who did that teaching the year before. They then train the fresh intake. So the academic staff would train one member of staff, one teaching assistant who did it last year perhaps. Then that teaching assistant spreads on their knowledge, and they'll probably even spread insight we haven't thought of because they'll have done it so much.
Yeah, so this Matteo method, I've adopted it myself for the first time this year. It's very powerful because you spend time with one teaching assistant, really tell them everything. And then when it's their job to teach the other teaching assistants, if they don't know something, it comes out in the wash and you really identify it. But the other really clever bit, and this was the thing I thought was absolute genius, is that between the lead GTA and the other subordinate GTAs, their job is to define how they're going to assess the lab. And they write that down in a document which they then share with us. So if they don't know what the learning outcomes are, they know about it at that point. So they really need to think about why the students are in that lab, because they have to write the assessment questions, which means they need to know. And once Matteo spends this time with the lead GTA then runs the sessions. So if he's got to deliver that 6 times, he's not in the lab anymore.
And 2 questions, sorry. Is being a GTA a voluntary thing, first? Second, do you use any technology to log in the hours of a GTA, or they have to use these old-fashioned forms like we use, like here, like keep on adding these up, then running behind lecturers to get it signed, then go to the office to...
It's voluntary but paid. And we have a machine because we work at scale.
The scanners that you do could be used for them to clock in.
Well, we have a dedicated member of staff to manage it, because if it was an individual department, they would just have a little ad hoc system. Because we put it all in one place, it makes sense to have somebody whose job it is to manage it. Advantages of scale. Okay, do you want to do one more? Or?
Yeah, there's one more. Any one
Teaching time.
teaching
I
time?
think that might be the GTA answer. So.
Cool. So we might have heard some of these things already.
Oh, okay.
Yes. Oh no, TA is on there. TA is on there. Again, it's so the sharing point here is coming from a different angle, I think, in that we're talking about building this shared facility that's shared across programs. If I design a great introductory session on electronics to deliver to bioengineering students, for example, so they're much less experienced than the electrical guys, but they need that basic introduction, then I've got that, and that's in the bag. So then next year, civil engineering come to me and say, we need an introduction for our guys. They know nothing about electronics. We can just share it straight on. And nobody complains. It's quite, because you're developing the best material and then just propagating it across the faculty at light speed, everyone is getting a higher quality experience. So in terms of time, yes, there is the time to deliver that in lab work, but actually what takes the time is developing the really good teaching material to start off with. And if you can then spread that over as many programs as you can, you're winning. Definitely winning. Pre and post labs is on there. We can't claim to have invented this, but we certainly perform it at scale, as we mentioned earlier. Anything that a student could do before they get there, we get them to do that. If that's pre-reading, if that's watching a video, if that's doing some calculations so they know what to expect. So actually some of our labs can be trimmed down from what used to be a 3-hour session, because they'd sit there and read the book and find the equation and do the maths. They did all that at home. 3 hours becomes 1 hour to take the measurements, write it all down, speak to a member of staff and just check and confirm their thinking is correct. Then they go home and they make the graph. So that 3-hour chunk that used to include everything could be trimmed right down. And again, the magic of our approach is that students buy into this a lot more and do it because they see it everywhere. So every single session has that kind of system in there.
I run a lab in the fluids lab teaching the Bernoulli principle, which is pretty straightforward, but I do it to a whole range of different engineers. And we do that in 1 hour. And that's for 80 students. We get them in the lab, we register all their attendance, they go and do the experiment, they come back, they process the results, they draw a graph, they talk to a teaching assistant, and they're out, and then we turn that around again. So in 3 hours, we can do 240 students. It's not one of these, it's not an open-ended investigative lab where they're going to fail, but it's not designed to be, because that in the program, that's not what it's there. It's there to just reinforce that one particular piece of content. So we say in 1 hour, we want them to learn one thing and then walk out. But we can only do that because we've got all these systems in place.
How do you enforce the free learning? Do you use your learning environment or yeah?
If they haven't done it, they can't walk in the door. They learn very quickly. Set up a culture. In fact, we've even got some memes on the university student Facebook thread where they've students, there's a picture of somebody crying outside a window and not being allowed in, and the meme on it saying, "I've not done the pre." You know, it's part of the culture now.
Do you actually like refuse them entry?
Yes. Yeah.
And
How do you quickly check it? To see whether they've done it?
We have a scanning system. We built it in-house because we could justify that because of the scale. The answer is always, if you do things at scale, you can justify investing in resources and building systems. Can't do it if you work individually. It's all about sharing is caring. Okay, should we move on? We can talk about these more either after this event or if we have some time.
Absolutely. So we can share with you later on. I imagine we can share with you this whole pack so you can see the answers to things that we didn't see. But we're going to move on because the bottom thing on here, teaching time, how to free up more teaching time, was to make more use of remote practicals. So that's what we're going to just spend the last little bit of this section on, is dealing with our remote work. So there we go. One thing I want to get forwards is another piece of terminology that we didn't deal with earlier. Remote practicals does not equal remote control. So you might think it's the kind of the gold standard, and we did that. I could give you another whole morning session about what we did in remote control equipment. This is kind of an example of kind of at the very beginning of COVID. We had loads of benches that weren't used in lockdown, or we had to separate things out for social distancing. So we just turned around the PC, so the webcam were facing the kit. You can see we're balancing bits of kit on bits of junk all over the place. We made it work just to deliver remote practicals. So we managed to turn that around quickly. We've had a bit of time. We've refined things. So this is now in the corner of my lab. We've got dedicated rack, lots of different experiments, all going on at the same time. But however shiny this looks as a solution, it has all of these problems. It cost us, in scale terms, it didn't cost us a lot of money. It was the order of tens of thousands to do it, but that's not achievable for everybody. Reliability, it still relies on a human to oversee it every now and then. We do have to check in with these systems, they're not infallible. Takes up less space than having all of this kit up permanently, but we had to get that racking in place. Maintenance, again, it's inflexible. So once we've set these systems up, they've just got to sit there running those experiments that we started with. And we went through a big old safety process to check that it was safe. So look, this thing here is quite a heavy metal flywheel that spins around, and making sure we could leave that running unattended and people weren't going to stick their fingers in. All those kind of things had to come into play. So remote practicals does not equal remote control. This is one way of doing it. It is most definitely not the only way of delivering practical skills remotely. What we need to do to deliver things remotely is match the delivery method we're going to use remotely. There's lots of different ways we deliver things to the activity learning outcome that we want to pull across. And this is best explained with some examples, I think, really. Imagine we want to teach data presentation. So one of our learning outcomes could be to get students to draw the perfect graph, get all of the labels in the right place, everything spot on perfect. Do they need to have done something hands-on to do that? Or could we kind of zip them through showing you a video, here's the experiment that we did, here's what we performed and why, here's the data set, go away and present to me the outcomes, make me the perfect graph, write me your conclusions paragraph on what happened. Did they need to do that hands-on task if the learning outcome I wanted was just to do the presentation? Not necessarily. Similarly, for measurement error and noise, often we want students to be able to quantify the errors and measurements that they make. Simulations are a brilliant tool for remote practical delivery. They're outstanding. But if your simulation is perfect, if your simulation spits out a perfect number at the end, if every student gets exactly the same number because it hasn't got a thorough noise model, that's not very useful for teaching measurement error and noise. So we need to think of another way of getting students to appreciate the limits of their instrumentation. We've got to line everything up with the LOs we want. I think my final example was about experimental design. So this is a learning outcome, might be for students to solve a problem using experimentation and design the experiment from scratch to find something out. Can they do that without getting hands-on with the equipment? And I think the image down there sort of represents one example of this. This is the one that Andrew made, but it shows all of the functions of a different piece of equipment. So they could look at all of the different parts of a piece of equipment, see its capability, see the ranges it could operate in, for example. Could they perform a design there, even if they don't get to go hands-on and do it? Could you still deliver that learning outcome of how to solve a problem using a particular set of kit? So we need to line up the delivery method remotely to the learning outcomes that we're trying to pull across. There are many, many options. These are examples from our practice at Sheffield of all the different remote practical options we use. So top left is just a video. So this is somebody doing the experiment in the lab. We film it. We put in a load of detailed captions explaining what was going on. We can have some audio as well. Underneath, a data set. So we couple these two things together. So video and a nice data set all in one place. Simulation. I've used two different images here. This is from the electronics world, so I apologize if you're not in this world. But the top is very much a kind of circuit diagram based model, and it's very thorough in how it works with noise, for example. So for an electronic engineer, they should be able to appreciate this little transistor amplifier circuit and be able to use this quite advanced tool that's kind of more on the professional side. There's also this tool here that looks like the things they would have got their hands on in the lab. So if what you wanted the students to learn from the activity was how to build a circuit on a breadboard and how to physically connect things up, you would pick this tool here over this more advanced professional tool. If your learning outcome was to be able to use a professional tool and then to get numerical results and perform some analysis, you'd probably go for this professional approach rather than this graphical blocks thing. It depends on the learning outcome you're trying to deliver remotely. These two here are different ways of doing the remote access. So this is what we just saw. This is the kind of the student vision of the remote accessible system. It's just one of our tools in our arsenal. The other thing we can do is live online sessions where a member of staff is there doing an experiment in real time and engaging with the students. So this took off in COVID because it was a great answer, but actually we still do it now and again, is run a live session where the staff member has got several webcams looking at all sorts of different things, different bits and pieces, and they can just pause at a moment and ask a question. They can wait for students to tell them what to do next, almost like having a remote control lab person to do what it is that you're trying to follow. The final two, we've got creating parts. So we can get students to send us designs to manufacture. So they can send us CAD files and we can do the 3D printing, we can do laser cutting, we can do all the kind of machining in the workshop. But students send us the designs they want us to make. And that means they have to work in quite a professional manner. So there's some kind of good skills there if you want. One of your learning outcomes is get students to communicate professional manufacturing techniques. They've got to give you the right CAD file, give you the right diagram, so that our staff can go away and make it, and then the students can come and pick it up. So it saves the students sitting in the lab and just waiting for things to happen, because they just submit their files, we make it, things move on. What that doesn't teach them is how to do the actual physical making. So they've got to appreciate how to communicate what they want. They've got to appreciate the limitations of the process, But if your learning outcomes are there, rather than in be able to use a 3D printer, be able to use a lathe, whatever, focus on what it is you want them to learn, take away anything they don't need to be doing that time. Final one, take-home kits. Everybody seems to have done this lately, but it depends on what you want the students to do. Take-home kits are fantastic. You can post out things for exactly what the students need to do, but it's very limited to what's inside this box, certainly. So, for example, we didn't send out soldering irons to our students, so we could not remotely teach soldering as a practical specific skill to my students. And we have to think of other ways to do that. The answer is to do that elsewhere in the program, because we hope they can come back and do it another time. But take-home kits can deliver as a subset of these things. Cool. So, summarising how to choose your delivery tactics, what we want to do is match the learning outcome. So don't try to directly recreate what students did in the lab. Think about the learning outcomes you wanted from the kind of an in-person thing, match it to something remote. Be feasible, so come up with something that's going to work. Can you afford it? Is the equipment going to work? Is it going to work for everybody and all of your learners? And if you want to assess that activity, make sure that it would work out. So is the remote activity you're getting students to do fair? Is it reliable for them all to get results? And does it actually kind of line up with the learning outcomes you want from the activity? Does the assessment all match up? Why am I telling you these kind of hints on what to do? Because our final activity for you all, Andrew's going to pass out some sheets to work in pairs or threes with some learning outcomes and some possible delivery methods. So we'll give you a few minutes just to try and match up some different learning outcomes. These are definitely activity level learning outcomes, and these are remote practical activity delivery methods. Match them up. Match them up. There's not necessarily one right answer. I've got some answers in mind, but as long as you can justify why you're delivering your remote practical that way, do it. Okay, we shall carefully have a look through what's been said. So again, don't worry if you didn't get them all, but let's just compare a handful of these things. So the top one I've got on my set: communicate data. Communicate data rapidly and in writing. Anyone want to shout out which one they went for?
Generate numerical results.
Generate numerical results. Anyone say anything different?
Yeah.
So there is no right answer, as I said, but I think both of those will be pretty wise choices, because it's all to do this communication activity. It doesn't say create your own data. It doesn't say perform an experiment to do that. It's all about just being given the data effectively. Now, the more engagingly you can give the students that data, brilliant. But that's a perfect way of doing that learning. Absolutely. Next up, independently design an experimental plan.
Household equipment.
Household equipment, nice. Yep. Any other ideas? Yes. Perfect. Perfect. So again, this is more about doing a thing, I suppose. So you're designing an experiment to solve a problem. If you know you're just using kit around your house, so measuring, cups and funnels and cylinders and things that students might have, you can design an experiment to do. I think you did a good one with kitchen stuff, didn't you?
Yep. The transition from laminar to turbulent flow in the tap in your kitchen.
There you go. There you go. So that's, but the students had to think about how they were going to do that based on the limits of what they had around them. But similarly, live online demonstration is perfect as well, because this doesn't necessarily mean they have to be carrying out the plan. They could be in remote control of somebody sat in the lab doing that experiment. So it's about identifying what it is we want them to learn. We want them to learn how to make a plan, therefore someone else can execute it. Cool. I'm going to skip ahead to the red ones because they were harder in the interest of time. So work as a team to experimentally solve a problem. What do we think?
Remote access equipment.
Nice, nice. But so this relies on having team access to remote access equipment, I suppose. But it's
so that they could collaborate and discuss at least.
Nice, nice. Any other ideas on the working of the team?
Interactive simulations.
Simulations are good, yeah. So this with the kind of team, you want everybody to be empowered together to see the same things. I think working as a team, certainly in the student land, it's all about equity often, isn't it? And often feeling that there's no passengers, no free riders, everyone can take part and be involved. So all of these options would work out fairly well, I think. Remote access would be great, but just making sure that everyone has access to it. The last red one, more difficult one, develop new instrumentation. What did we think?
Take home kits, household equipment.
Yeah, yes, and again, so this is very much a hands-on one, I think. So this one about is a little bit more difficult for students to do without.
Staff manufacturing service.
That was going to be my suggestion. Yes, absolutely. Staff manufacturing. So if students can then have the dialogue with staff about how it is they're going to create this new tool, you know, you can say, I want you to laser cut me this piece of kit to, you know, 2 mil tolerance. Can you do that? Staff says, no, I cannot, but I can offer you this. And there's just this back and forth professional dialogue about the capabilities of different processes. It doesn't mean, again, it doesn't necessarily mean they have to have made that piece of instrumentation, but they've learned so much about instrumentation and measurement along the way, and tolerances and things like that everything fits together nicely. Excellent.
How would you just use specific equipment? Is that, would you consider that interactive simulation, like an oscilloscope or?
So it depends on the simulation. So if you build a simulation that reflects the equipment that you've got, perfect. It doesn't have to be like for like. It can be like the functionality level rather than specific detail. I tend to go for remote access purely because I've got the facility to do that. So what I've done with lots of my teaching is lined up the lab sheet that a student would do in the lab with the same capability in the remote access system. So they could do 99% exactly the same activity whether they do it in person or they do it online later, because I've still got exactly the same instructions on how to use an oscilloscope. Press this button, press this button, press this button. Then you use some clever tricks with the remote kit to say, okay, we've reset everything, giving you a new signal to measure. Set it up, make the measurement, type it in, see how you control. But that's
and then
specific to
that
my
with
role.
the physical tactile nature, you know.
Yes. Yes.
You looked at that, or you know,
yes,
the
it's
outcome
true.
of that is.
So the beauty of this is we have to take it back to the learning outcome mapping again. Yeah. So if you think across your whole program, firstly, I think it would be awful if we took out all of our hands-on in-person labs and did everything remotely. I think that wouldn't work out. But at a program level, if you think some of these are going remote, some of these are going in person, you've got a balanced diet across everything. And that kind of ties in nicely to kind of my picture.
Segue there.
Aha. So this is very good. We have 6 tactics across everything we did at a faculty level. So we did, as we explained earlier, we teach practicals across a whole faculty, and we've got a department of 15 academic staff. We looked at everything we did in response to COVID, all the different ways of doing things, and we found we could have 6 broad groups of ways to do this. We'll share this with you afterwards so you can digest, but this kind of pattern of using 6 broad headings can really help us with planning, so that across your whole program, when you do a learning outcome mapping exercise, if you find you're too heavy, really heavy in one way of remote teaching, if you're really heavy in remote versus in person, you can map everything together. So digital artifacts, video and data, simulations, but you have to think a little bit about what your simulation is showing you. Synchronous participation includes both the student taking control and the student just instructing staff on what to do. Alternative environment was take-home kits or your own equipment. Staff manufacturing, but also the one key one is how to make sure staff can support all of these things. So it kind of ties into all of the other 5 things, is if a student gets something wrong, if a student doesn't understand what they do next. If a student is spending 10 hours on something we assumed they would get wrapped up in 90 minutes, how can we try and replicate that really structured and well-designed teaching with staff support? That's the only thing we didn't cover in these earlier options. If we do all of what I was going to ask you was, we can call them out, I suppose, very quickly. You did an exercise. The first thing you did here was find the density of the cone there. How would you replicate that in a remote world out of these 6 categories of things? What would you replace? Household equipment? Yep. Any other suggestions?
Alternative environment.
Yeah. Yep. Which is that. So that includes the household equipment because you're doing it in household equipment. Absolutely. Slightly trick question though. What was the learning outcome we wanted you to do from this? Were we interested in that final number you got? Were we interested in the precision and accuracy you could tell us that? So maybe precision in particular that you could tell us that measurement to? Were we interested in looking at how you designed your experimental plan to get there? So even just in that small activity, there could have been many things that we could have chosen the learning outcome, what we wanted you to do. Pick your learning outcome first, then pick your way to deliver it. So overall, this is my vision for the future of labs, I suppose. The traditional labs, pre-lab, you read the lab script before you come in. In the lab, you come in, you do the in-person activity. Post-lab, you do some sort of written report, quiz to show you understood what you did. Actually, using all of these things, it becomes remote enhanced, if you like. So there's still an in-person experience at the center of most of these things, or an online alternative. But instead of just reading the lab script before you come, why not do a simulation? Why not talk to staff about manufacturing the piece of equipment that you're then going to use later on? And the experiment doesn't have to finish at 5 o'clock when the lab closes, because you could follow up using the home kit, follow up using telemetry, remote access equipment. Everything is kind of one big seamless picture between the in-person teaching and the remote. Excellent. That concludes remote practicals, I think, and that concludes our time for today. We know it's almost at the end, but before we finish, we thought it was really important to just take a moment to think and reflect on what has happened, what we've learned. So what we'd like you to do is just we'll time it for just a few seconds. Andrew will set a timer. Think on your own, perhaps, and then maybe share it. But just think on your own. What are you going to take away from this session? How is this going to impact on your practice going forwards? And Andrew will set a
60 seconds.
60-second timer. So just reflect for yourself first, and then maybe share when you're comfortable. How is this going to impact on what you do when you go back to your own labs? You go.
Yeah, we did have an answer to this for assessing skills in one of our pre-prepared slides, but we're trying to popularise this idea of what we call threshold assessment, which is this idea that when you have a learning outcome, you're essentially trying to do two jobs. You're showing that students have met the learning outcomes, and you're differentiating them, the best from the worst. Actually, what you tend to do is score people on a 0 to 100, and anything less than this threshold number is a fail. Actually, for things like lab skills, do we care if somebody's really good at operating an oscilloscope, or do they just need this threshold level of skill? Yeah. So what we tend to do is we have a 40% mark on our modules that are 0 or 40. There's no differentiation. You either pass or you don't, which makes assessing really easy. And then we decide what makes what we consider to be, we call it mastery, what differentiates a good engineer from a bad one, and that's the remaining 60%. So that threshold assessment, and we've also got something called spiral staircase model, which I could talk you through, but we don't really have time. Good. In the interest of time, I think we'll quickly flip through because we are running slightly over. Can we go to actual planning? Yeah. Okay. So if we'd have had time, we would have populated this, but actually, I think eternally you can commit. What actions are you going to take away? Who's going to do them and by when? Another thing that we do in our department is whenever we are applying an action that needs to be done, we just take a minute to think about any ED&I aspects, and if you can think of the work, which protected group is going to be most impacted by this. If there's nothing you can think of, then it's probably okay, but it's worth reflecting on. And lastly, we'd just like to thank you for coming, and we do have an evaluation which I'm sure will be circulated afterwards, but we'd really value your feedback as to whether or not you've found it enjoyable and useful. But other than that, it's bye from me. Yeah, thank you very much.